Okay, so last lecture we were looking at application of quantum mechanics, quantum physics to understand solids, and we had started off with this particular equation, Schrodinger's equation. We said that if you solve this equation for a particle or a system of particles, you end up getting wave function psi, and through this wave function you can obtain whatever quantities of interest are there. You can obtain it from the wave function itself. And and the wave function, of course, has a spatial part here and a time part here, which is given over here, which is for stationary states here. All right. So what we had obtained is the following: we had applied Schrodinger's equation to a few simple problems. One of them was a finite quantum well, meaning that the potential energy is 0 here, potential energy is some finite value here, and the electron energy is less than the potential energy here, so it's sort of trapped. That's why we are calling it a well. So it's trapped inside this particular well here, and we saw that the wave function has a form of this particular kind here. The electron, of course, is in this particular energy state E1, whose value we can calculate from Schrodinger's equation, and we call such a state, we also call it a localized state because, as I said, the electron is trapped inside this particular well. You can see that there is a finite probability of finding an electron here or an electron here, but the probability decays and is pretty much in this particular well here. We also saw that if you take a quantum well like this and you couple it to several other quantum wells, then what happens is, as a result of interaction between these wells here, what you get is a series of energy states, and the original energy that you see here, it splits into several energy levels. If you have two couple quantum wells, you get 2 energy levels. If you have n, you'll get n energy levels, all closely spaced to each other here. Okay, and so this energy level E1, it expands into a band. Not only that, the wave function that you see here, which was localized, the wave function now spreads over the entire, if you can think of this entire one-dimensional lattice here. So the wave function now, the electron is no longer confined to this particular well or to this particular well, is sort of free. You can see here the probability of finding an electron here or here or here is the same. All right. So the electron is now spread over the entire lattice here, and that's what we call it as a delocalized state. So the electron is no longer confined to a particular well. The electron can now move from one well to the next and so on and so forth here. Okay. And you can see here the wave function, that's like a propagating wave function here as compared to a decaying wave function here. So the electron is localized here. All right. So aside from that, we said that if a simple quantum well has 2 energy states, E1 and E2, these energy states, they expand into bands here. Each one becomes a band of energies here. E2 will also become a band of energies here. And so that's the other thing that we saw here. All right. So let's continue our discussion. So as I said, our goal is to understand how electron behaves in a solid. And all these simple examples we are looking at in an effort to arrive at some understanding. Again, as I said, the focus is more on, developing a quick qualitative understanding, because quantitative understanding and rigor requires a lot of maths and a lot more time. Okay, so the idea is many of the things that I will talk about and state, I'm sure these are important concepts. They'll raise a lot of questions in your mind, and it's not possible to arrive at, as I said, a good complete understanding through the 1 or 2 lectures that I'm going to give. If you want to do that, then you have to take a separate course on, say, solid state physics, which goes into these things in more detail here. All right. So anyway, so the goal is to become a little bit more familiar with these important aspects. That's all that will happen at the end of the lectures here. All right. So let's look at, we saw an electron inside a infinite quantum well. We saw an electron inside a finite well. Let's look at a free electron. I mean, what I'm going to talk about is true for a free particle, not just an electron here. So free in the sense, so note that this is the Schrodinger's equation that we have. The total wave function has a spatial part and a time part. Spatial part is here. Time part is here. All right. Free electron means that there's no force acting upon it, which implies, let's say, the potential energy is 0. All right. So the electron is not under the influence of any potential energy. Let's assume this equal to be 0, right? So it's free. And for that, then let's solve the wave function here. So Vx is 0. And the solution is straightforward. Minus h bar square by 2m del square psi del x square will be equal to E psi here. We take h bar square by 2m to the right hand side. We write it as k, where k is written as square root 2me by h bar square here. So we have a simple first order differential equation, and whose solution is of the form of a exponent ikx here, right? So straightforward solution. Will not go into the details of what a is and all that. So we get a psi equal to a exponent ikx here. And if I look at the time part here, I can multiply them together. So the total wave function turns out to be a exponent ikx exponent minus I e by h bar t. So for a free electron, then my wave function is of this particular kind here. And if you look at this particular wave function, it should remind you of something, right? A plane wave. A plane wave, if you recall, plane wave is nothing but y equal to the amplitude y equal to a exponent ikx minus omega t. So you can see a clear that this equation that you got is nothing but that of a plane wave. But then this is not a, here we are not talking about actual amplitudes and all that. We are talking about a probability wave. That's what it is. So what it says is a free electron is like a wave with a certain wave vector, which indicates the direction in which the electron is moving. All right, just like a wave, k denotes the direction in which the wave is propagating. So k here denotes the direction in which electron is moving here. And so the electron can be then modeled as a sort of a plane wave that you see over here with a certain wave vector and with a certain energy associated with it. Okay. All right, let's proceed with this. So this is the picture that quantum mechanics is telling us. And the wave vector k is related to energy through this relationship here. All right, which I can rewrite it as E equal to h bar square k square by 2m. All right, so the model of a free electron that quantum mechanics is telling us is that of a probability wave here with a certain wave vector k, with a certain energy E, and the wave vector k and the energy E are related through this h bar square k square by 2m relationship here, which is shown over here, right? So it's a parabolic relationship here. Some certain other things that the quantum mechanics is telling us, it tells us, for, as I said, momentum is P equal to h bar k, momentum of the electron. As I said in the very beginning, that if you know psi, then quantum mechanics tells us that you can derive everything else about that particular particle here. So from this psi, I can derive and show that the quantum the momentum of the electron is h bar k. The electron velocity, I can write it as 1 by h bar del E by del k, and it turns out to be h bar k by m. If I take this ek relationship here, E versus k, and I take the derivative, it gives us h bar k by m here. And it seems to make sense here because E is h bar square k square by 2m. If you say momentum is h bar k here, so you know that momentum is p square by 2m. That's what you expect here. Velocity is h bar k by m, so momentum divided by mass. So velocity also makes sense here. And if some of you are wondering why I took v equal to 1 by h bar del E by del k as velocity here, if you recall, for a wave, the velocity v equal to del omega by del k. So if you use that analogy, you can see that you'll arrive at this particular expression for this is for wave velocity here. You'll arrive at an expression for the electron velocity here. All right. And again, for all these things, one can, for example, P equal to h bar k, I can go ahead and do a bit of more calculation and show you how P equal to h bar k comes about. But the main goal is to understand what quantum mechanics is telling us with as little mass, as little derivation, as what is quantum mechanics telling us about a free electron. It's telling us that view a free electron as like a wave here, with a certain wave vector k, with a certain energy E. And E and the wave vector are related through this relationship. That's very important, that E and K are related through this E versus K relationship, which is parabolic. That's a free electron. And again, P equal to h bar k, and the velocity is h bar k by m. Okay. A little bit more, let's do a little bit more simple calculation based on this here. So if you take P equal to h bar k as a momentum, and you know, the derivations that I'm doing are a blend of classical and quantum mechanics. As I said, rigor is not there. The goal is not rigor, but the goal is to arrive at the final understanding here. Okay, so P equal to h bar k here, And note that external force acting upon an electron should be dp by dt. And therefore, I can write h bar dk by dt here, right? That's the external force. So what does an external force do to an electron? According to quantum mechanical picture, what it does is, say I apply an electric field. So there will be a certain external force acting upon the electron. What does it do? It will change the k, the wave vector, as you can see here, dk by dt. So wave vector k will change. And as the wave vector k changes, note that E equal to h bar square k square by 2m. The energy of the electron will change. All right. So that's how the electron is responding here. Also, I can write, you know it classically, if external force is m dv by dt. All right. So, and v we have seen is 1 by h bar del E by del k. Right. So what I can do is, I can take this velocity, plug it here, and I can get another expression through this route here by writing force is equal to m dv by dt, v equal to 1 by h bar del E by del k. I can get another expression for force here, and force external can be written as mass here. And dv by dt, all that we have done is written in terms of, taken one more derivative and written in terms of dk by dt. Okay. So taking a derivative del by del k and then del k by del t. Okay. So we write this one here. So we get an expression for external force acting upon an electron, which is over here. And if we compare the two together here, these two equations here, what we are finding is dk by dt is common here. What we are finding is, which you will see many times in semiconductors, what we are finding is that the mass of an electron is related to the double derivative of E versus K here. So M I can write as h bar square del square E by del K square. Okay, it's just a relationship that we have derived, and this will prove to be useful later on, as we'll see. Okay, so a relationship between mass and the double derivative of E versus K relationship here. All right, let's continue. Say I give you two EK relationships. Now this I'm talking in terms of electron, but note that it's true for any free particle. Any free particle, this relationship is true here. So if I talk of E versus K relationship and I give you two EK diagrams here, both are parabolic, one here black and one red here. Both are free particles, and which one has a higher mass? Which one has a higher mass? We have a particle of mass m1 and a particle of mass m2. M1 is higher mass. Everybody sees that? Well, one, of course, we'll get it from here. M equal to h bar square del square E by del K square. You can take a double derivative and see that M1 is higher than M2. How else we can say? Note that if an external force acts, what does it do? What does it change? Go back and see. What does it change? K. And the change in K is independent of particle mass. Right? So if I have an external force acting, let's say K is 0 here, the K goes here somewhere. Same K will happen for both the masses. One mass acquires energy so much, the other acquires energy so much here. So from there also you can see which one will be lighter. All right, same K that they go here, same momentum that they acquire here. One acquires an energy this much here. For the same K, one acquires an energy here, the other one acquires an energy here. So remember, K is nothing but momentum. So which one will have a higher? Without going into curvature and all that, you can also see that an external force will cause the K to change by the same value here. Go and read the energy here. Go and read the energy here. And note that energy is nothing but related to K here. Momentum divided by mass here. So from there also you can argue that M2 is lighter than M1 here. All right. Okay. So the summary of a free electron is important for us is the following. View a free electron like a wave here, plane wave, probability wave here, E equal to h bar square K square by 2m. That's the relationship between the wave vector and the energy here. Momentum is h bar K. Velocity is given by h bar K by m with a more general expression here. And mass is related to the curvature through this expression. Now, so free electron, of course, we are interested in electron in a solid. Right, in a silicon crystal or a germanium or gallium arsenide. So we are interested in electron in a solid here. So how is this free electron picture important for us? Okay. Now suppose electron, let's say in some solid or some system, has the following characteristics. That is, suppose there's an electron moving in a solid, right? And by some means, I arrive at this E by K relationship. I solve Schrodinger's equation for an electron inside that particular solid, and the Schrodinger equation will give me E versus K relationship. Why? Because we are talking about a big solid here. The electron we have seen is free to move around in the solid. Okay, so you can think of electron moving around in the solid here. And let's say I get an E versus K relationship like this. Okay, by some means I get that here. Now, it's not parabolic. What is the signature of a free electron? This one here. That's the signature of a free electron. E versus K going like this here. Right? Parabolic relationship here. This is not parabolic here. This is quite different here that you can see here. All right. So my electron obviously moving in a solid is under the influence of forces inside a solid. A lattice will have positively charged atoms and all that. So it's moving under some potential energy, right? So it's not free in that sense. It's not free. It's moving under some potential energy surface here. While here, of course, is free. So obviously I expect differences between this E versus K relationship versus this one. But note that if I find that my electron stays, let's say, very close to the bottom here, very close to the bottom here most of the time, let's say is very close to the bottom here. And if at the bottom here, note, if I can approximate it by, by a parabola here. Approximately by saying it's a parabola here at the bottom. The whole curve, of course, is not a parabola, right? But near the origin, maybe I can approximate it by a parabola and say E equal to CK square, right? Note that there is a minima here, and therefore if you have any E versus K relationship and you do a Taylor series expansion, and if it's near a minima, the first derivative goes to 0, and then the next simplest approximation to the profile would be CK square. And of course, note that I will get K cube and all that. Okay, so if I expand, but if I stay very close to the origin here, K, then this whole EK relationship can be thought of as a parabola, E equal to CK square, right? So I can approximate it. It's an approximation. I can approximate it like this here. Now, can you see it is pointing to something very interesting? E equal to CK square. What is it beginning to look like? It's beginning to look like this EK relationship, parabolic, which means what? That I can think of this electron inside the solid as if it is free, but what? Note, having a different mass. This, how was E in a free electron? E was equal to h bar square K square divided by 2m. I don't have that h bar square by 2m and all that. I have some constant here, c, right? So what I do is, it implies that near the origin, the electron can be modeled as a free electron, but with a different mass. Okay? So this is the analogy that we are building. This is my free electron. All these things that you see about a free electron. And what we are saying is E equal to ck square near the origin. And C is not equal to h bar square by 2m. It's not free, mind you. Right? But what I can do is I can think of this electron here as a free electron, but with a certain mass. And how much mass will be there? Well, I just equate C to h bar square by 2m, and then I get a mass which is equal to, another way of calculating mass would be take a double derivative, h bar square by del square E by del K square. So I get a mass here which is h bar square by 2C. So what it is saying is the following. My electron in a solid close to the origin here, close to K equal to 0, can be thought of as a free electron, but with an effective mass here, m star. Effective mass of how much? Depending on what the curvature here at this particular point is. H bar square by 2C here. Okay. So this is a very, very powerful concept in semiconductors. What it is saying is, if I have a electron moving inside a lattice or a solid, right? And what it is saying is that you can remove the effects of the lattice altogether. What does a lattice do? Lattice will create some potential energy surface, right? You can remove the effects of the lattice altogether, at least for in some cases where it's very close here. You can remove the effects of the lattice. Think of electron as completely free, but with an effective mass. All right. So all the effects of the lattice is all subsumed in this concept of effective mass, m star. Now you add some external force upon it. Now you can think of my electron is free, right? Electron is free, and you add an external force to it, and the electron moves just like a free electron, but with an effective mass m star. Okay, so very, very powerful concept, and it's coming from analogy with this free electron picture here. What one is saying is one will approximate this by a parabola here. Now, of course, as the note that as you apply a force, K increases here. It may happen that as you apply a force, K may go over here. And then, of course, what it means is your effective mass approximation is breaking down. All right. But we'll do some simple calculations and show you that under typical cases, that K will lie very close to the bottom. Okay, we'll show you that. Okay, so the electron, the takeaway from here is the electron can be considered as a free, but with an effective mass m star here. Okay. Of course, once you approximate it as an effective mass, all the expressions that are there for a free electron are valid here also. So, for example, P equal to h bar k. I can write now for my electron some P, let's say C equal to h bar k here. Now note, when I write it equal to h bar k, this has the units of momentum. It's not the real momentum of an electron, but it acts in all aspects like a momentum here. Because note, when my electron is moving inside the crystal, it's moving under some forces, right? So those forces are already there acting upon the electron, but all its effects I've taken into m star here, right? So now Pc equal to h bar k it acts like a momentum, and when you apply an external force, this Pc here or h bar k changes in response to the external force, just like a free electron here. But don't confuse h bar k now as the total momentum of an electron. Is not. Okay, and that's why people use the word, sometimes they add here, because the electron is moving in a crystal, they add the phrase crystal momentum. It's the momentum of an electron, some effective momentum inside a crystal here, to denote the fact or to separate it from the fact that it's not the total momentum. This is only a model. We are modeling an electron as a free, and therefore we are saying Pc is equal to h bar k, and all of this is valid here. Okay. This is also bringing to you the importance of, in semiconductors, energy versus wave vector relationship here. That E versus K relationship is very important. And for example, E versus K relationship decides here what the effective mass of the electron is. Okay. Different semiconductors will have different energy versus wave vector relationship and different behavior. Okay. All right. Let's go a little bit in more detail into this here. Let's look at a one-dimensional periodic lattice here. Okay, so you may imagine a lattice, something like this here. These are the nucleus here, and you have a Coulombic force here. Coulombic force here, and of course, the atoms are very close to each other, so the forces are, the energies are interacting with each other, and you may imagine a lattice looking something like this here. Okay, even though it may be a one-dimensional lattice, solving Schrodinger's equation with a Coulombic well is difficult. And so the simplest picture of a lattice that one can build, the first approximation is that it's 1D. We have not taken the other two dimensions. The other approximation that we can make, the simplest lattice that I can build, is not take a Coulombic well, but approximate it as a rectangular one. Okay. All right. Before I do that, approximate it as, there is a theorem which is named after the person who proposed it, called Bloch's theorem here. What he says is the following: when an electron is moving in a periodic potential, right, periodic potential energy that you see here, the wave function of an electron, this can be derived and shown to be true. What he said is that the wave function of an electron has a part exponent ikx, and which is that of a propagating wave, and along with that there's another part here, ukx here. And what he said was this part here is periodic. UKX is equal to UKX plus NA A naught. A naught is the lattice constant here. So what is, you can imagine that if I didn't have a periodic potential, we know that psi x is simply exponent IKX here, right? Is simply exponent IKX. When you have a periodic potential, in addition to exponent IKX, what you get is this additional part here, which is also periodic in nature. So that comes from a theorem named after him called Bloch's theorem. Again, note that the time part is e to the power minus e by h bar t here. So if you multiply it together, what you see is, again, it's like a wave, but this part you could think of as a modulating function. right? If I didn't have this, if this were a constant here, then it's like a simple plane wave here. But now this additional part here, you could think of it as a modulated wave with some kind of a modulating function here. And the modulating function is periodic in nature. Okay, so some kind of a modulating function. But again, the picture that we have of an electron inside a 1D periodic potential or periodic lattice is a picture of a wave. The wave function is that of a wave with a certain wave vector k, with a certain energy E. Again, of course, it's not a simple plane wave. There's something else in addition to it. And that's why the E versus K relationship is not simply h bar square K square by 2m. It will be more complicated because of the periodic potential that you see here and something like this coming up. Okay, so that's Bloch's theorem here. But as I said, even if I take this 1D lattice with a Coulombic potential, it's difficult to solve solve this particular problem analytically. So the simplest problem that one can think of is approximated by a lattice like this here. Okay, so this Coulombic well is being approximated as a finite quantum well here. And then, so note that there is a well here, well is over here, and then there is a barrier part here. The electron cannot just, the electron sees a barrier here, so the barrier part is here. And as a general problem, one can take the well width as A and the barrier width as B here. And therefore, what one has to do is now solve for this particular lattice here. And so this view of a 1D lattice that you see here being approximated by these rectangular wells is what we call as a Kronig Penney model, after the name of the people who first conceptualize it and solve this particular problem here. So in a way, the simplest lattice that you can think of is this one here. Simplest lattice is 1D in nature, and the potential that you approximated by a simple rectangular potential. There's nothing that can be simpler than this here. Okay, so Kronig Penney model gives us the simplest view of a lattice, and it's something that if you give me 2 days time, I can solve this in more detail because the methods are. I'll just show you the method. The methods are very simple, conceptually very simple, but then the maths becomes a little bit tedious, and one has to go through it. But I'll give you the outlines of it, okay? And if for those of you who are interested, can read more about it in the books here. So the idea in all of this is as follows. I have Schrodinger's equation, which I want to solve. So remember what we do. We solve it in this region here. You can see clearly there's a region from x equal to 0 to a. That's one region here. Okay. So we solve Schrodinger's equation here. Without going into the details, we write down Schrodinger's equation and we get a wave function and all that. Then we write Schrodinger's equation in the region 0 to minus b here. That part here. So we write it there also. All right. And we write it and we get a solution there also. Okay. In this region here. Now, of course, the whole thing is periodic, right? The whole potential is periodic. So after that, what we do is we do boundary conditions. We match the boundary conditions here. We match the boundary condition. We say the wave function here in this well must be the same as the wave function that is coming from this side here. So this is true here. The derivatives must match here. And we also apply the Bloch's theorem. The Bloch's theorem, remember, told us that the wave function is also periodic. So whatever is the value of the wave function, let's say at a, here at this point, must be the value at this point here multiplied by e to the power I k a plus b here. So we apply Bloch's theorem here. So that gives us other boundary condition. So we write down all of these conditions and we solve it. We'll get certain constraints. And at the end of all, what we get is, all these boundary conditions are there. So we do that. At the end of it, let me skip all this. At the end of it, what you get is a certain constraint. Remember the problems that we solved earlier. For an infinite quantum well, we got a constraint, right? The constraint was k times L was n pi. Similarly, for a finite quantum well, we got some constraints here. So this is the constraint that we get. Our solutions must obey. Okay, so there's a long equation that you see here. Look at the terms in the equation here. Okay, so there is a small epsilon here. Epsilon denotes as the total energy E of an electron normalized by the potential well height here, V naught. Alpha naught is square root 2m V naught by h bar square. So alpha naught is a constant. Alpha naught is a constant. V naught is given to us, right? And then we have energy E. And along with that, what do we have? We have K, the wave vector. All right. We have the wave vector here. And what we need to do is we need to solve this particular equation, and the solutions will tell us what values of energy are allowed, what values of energy are not allowed. In all of these systems, we found that in a infinite quantum well, we got discrete energy levels. Some energies were allowed, some were not allowed here. Similarly, in finite quantum well, and similarly here. So all that I had was Schrodinger equation written in two different regions, and after matching boundary conditions, what we end up with is an equation like this here. Okay, so now what we need to do is find solution. Note that our wave function is of this form, ukx exponent ikx here. K denotes the wave vector here. So note that for different values of k, suppose I put k as some value here, I will get a solution for E. That's what it is. I'll get a solution for E. So in effect, what am I getting from this solution? E versus K relationship. That's what I'm getting. Okay. So let's do that here. So one of the ways of solving this particular equation is you take left hand side and you take right hand side and you plot them together and see where they intersect here. So given this particular equation, you can easily go into MATLAB and plot this out. This particular equation for different values of this normalized energy here. Energy normalized by V naught here. So x-axis is E by V naught, and you plot left hand side. And you find left hand side, obviously, because you have sine and cos and sine hyperbolic, you see there is a periodicity here. So it goes like this here. The black line is the left hand side here. Okay. That's this particular equation here. The right hand side is cos k a naught. And obviously, because it's a cos function, and note we are solving for real values of k, propagating wave functions. And so this cos k a naught must lie between +1 and -1. So I've drawn one line here, +1, and I've drawn one line -1 here. And therefore, for any, the value of the left hand side between +1 and -1, all these are allowed values. They will satisfy your equation. Okay, they will satisfy your equation. So what we are getting is the following from here. We are finding that there is a whole range of solutions possible in this region. For note that each one represents a certain energy. So this one represents an energy here. There is a possible solution. And similarly, as I go here, I get a range of solutions till I reach this particular point here. What does this point represent? This point represents +1. +1 is like k equal to 0. So this particular point is for k equal to 0. Now, at this point, my cos becomes -1. So what is k? Pi by a naught. K is pi by a naught. So I start from k equal to 0 and I go to pi by a naught. I'm going from +1 to -1, and all these are allowed energy levels. They're giving me a solution. In between, I'm finding there's no solution here. Why? Because my left hand side is greater than -1 here. No solution. None of these energy levels are allowed. And then again, it becomes less than -1. So all these energies are allowed here. But again, it becomes more than +1 here. So again, these energy levels are not allowed. So what I'm getting out of a solution of Schrodinger equation for this 1D lattice, I'm getting that there's a band of energies which is allowed, and then there is a band which is not allowed. Another band allowed, another band not allowed. So I'm getting, it's just coming out as a band, a series of bands in my solid here. One band here, another band here, another band here. Okay, so all these are allowed energy bands. And in between, I have my forbidden bands here. Okay. Now, this is exactly the same that we had done with a finite quantum well. In a finite quantum well also, except that we had some constraint, left-hand side, right-hand side, we plotted, we got only 2 energy values, which were allowed. Those discrete energy values have become what? Now we get a band of energy values which are allowed. Okay. So as I go from a single finite quantum well to a 1D lattice, this is what is happening. One energy level is becoming a band here. Another energy level is also becoming a band here. Okay. After a while, you may see that this function here, you can see here, this function may lie entirely between +1 and -1, which means after that I have a continuum. All allowed energy levels. Okay. In this case, eventually that may happen. All right. So this is a picture that I have now. Okay. So for a 1D lattice described by the Kronig Penney model, what I'm seeing here is that I'm getting a series of bands here. Now, these bands that you see here, what does this band represent? It represents that for a particular value of k, I have a particular value of energy. That's what is represented. So, for example, I can represent these bands now like this here. Let's see if this picture makes sense here. This is my blue band, the lowest energy band here. In the E versus K relationship is shown like this here. This is my red band here. Next higher band is shown like this here. And then my next band, higher band here, is shown by the green one. Let's see whether it makes sense here. So remember we said you start from K equal to 0 here, right? K equal to 0. So K equal to 0 here. Somewhere some energy is there. Now as you go from K to higher and higher values, what is happening to the energy? You're increasing, right? You're going higher and higher energy. Eventually, so you're increasing in some form. We don't know. It is just qualitatively drawn. Okay, you're going here. Eventually, as you reach K equal to pi by A naught, you reach this end here, -1. So K equal to pi by A naught, you reach this particular end here. All right. So you see this energy rising like this here. Now, whatever I write for note for K positive in a 1D lattice, energy for an electron going in positive K or minus K has to be the same from symmetry. So whatever and it comes out from here also, I can put K equal to minus pi by A also, 0 or whatever, minus direction also. So you can see there's a symmetry here. So what you get is after pi by A naught, because the function is periodic, so it just repeats itself. Okay. So you only need to show K in a region, pi by A naught and minus pi by A naught, because after that it simply, it repeats itself. That's it. It's a periodic function. Okay. So anyway, so this band that you see here, this band is nothing but this E versus K relationship that comes out. E versus K relationship that you see. Okay. So that's this particular band. The next band that you see here, it starts from -1. -1 what means? Pi by A naught. So it starts from here, pi by A naught here. And then it starts from here. And then as I keep on increasing, it goes towards here. So what I'm doing is I'm starting from here and then going here. Eventually, when I come to this end, it goes to +1, which is 0 here. So I start from here and then I go up here. And of course, it's symmetrical. So I come here. Once I do that, then the next band that you see here starts from K equal to 0. So I start from here, K equal to 0 here, and then it goes up here. So that's why if you're wondering, one band looks like this here, the other goes like this here. And then the third goes like this here, and the fourth will go like this here. So you get a series of bands here, and for each band that you see here, there's a particular E versus K relationship here. Okay, particular E versus K relationship and that you see. Okay, and this is the band represented in energy versus momentum. K is like a momentum, energy versus momentum space. This is band just simply represented in the spatial domain by saying I have a band. So in this case, note that the x direction is space, spatial coordinate here. They're simply showing there's a band here, and then there's a band here, and there's a band here. So this is in energy versus x domain here, and this is energy versus momentum space domain here. So this is how my bands look like. Okay, so I get a series of bands that you see here. All right, what do we do with these bands here? And in each one of them, note, in each band, my solution is of this form here. Psi x equal to ukx, that's what the Bloch's theorem tells us. Bloch's theorem tells us that the wave functions are of this particular kind here. Exponent ikx is a wave part here, some modulating function here. And this is, of course, is always there for stationary states, minus I e by h bar t. So it's like a plane wave, but with some modulating function that you see. Okay, so the picture of an electron in a 1D lattice that we are getting is like a plane wave with a certain wave vector k and with a certain energy E, right? Except that my energies now exist in bands. I have a band of energies which are allowed here, this band and this band and this band here. That's what Kronig Penney model is telling us. Now in a more complicated lattice, same thing happens, except that my E versus K, the problem becomes three-dimensional. K can be in various directions, you can imagine. 1, 0, 0, 1, 1, 0, and 1, 1, 1. Different directions are there. And you get a three-dimensional. This is not a one-dimensional diagram. You get a three-dimensional diagram. Okay. So things become more complicated. I'll show you a typical E versus K diagram for silicon later on here. All right. So the picture is then a wave here with us again with a wave vector K with a certain energy E and E versus K relationship. You get from by solving Schrodinger's equation, and for a 1D lattice is something like this here. Okay. I have an example here. With a certain, say, the potential was 2 volt, 2 electron volt here potential. A naught was fixed at 5 angstrom, and B, the separation between the two wells was changed. So what you find is that, and what we are looking at is the first band, the width of the first band, E1 and E2. E1 is the lowest energy level, E2 is the highest energy level. So I'm looking at E2 minus E1. So you can see here, if the separation between the wells is large, not too large, 5, let's say here, the width of the band is 0.063 eV. As the separation between the wells reduces 4, the width of the band increases 3, 2, 1. As the wells get closer and closer together, the width of the band becomes higher and higher here. So when you have a separation which is only 1 angstrom, the width of the band is 0.77 eV here. Anyway, so it tells us obviously that how the bands here, the width of the band, how it changes with the interaction between the wells. And obviously we expect that if B becomes very, very large, what will happen? If B becomes very, very large, E2 minus E1 will go to 0. And what do I get? Discrete energy levels. That's what is happening. So in the limit, you will see that you will get a discrete energy level, discrete energy level, discrete energy level. Each well will have its own discrete level, which is the same throughout. Now, as the interaction between the wells is increasing, as B is decreasing, the wells are expanding into a band. The wells are expanding into a band, and the width of the band increases as you increase the interaction between the wells here. Okay, it becomes wider and wider and all. Okay. Now, here is something now. Let's see what we can do with this particular band here. So so we get a series of bands. And as you would expect now, all the electrons that are there in my lattice would now occupy these particular series of bands there, right? Like in an atom, you have, it fills up 1s, 2s, 2p, 3s and all that. Similarly, the total number of electrons that I will have, they'll first go and occupy all these lowest energy levels. Once they're full, then they'll go ahead and occupy these energy level, this band here. After this is full, then they'll occupy the next, and they'll fill up just like they fill up from lower to higher. Similarly, they'll fill up from lower to higher bands here, right? So you can imagine that I have a band which is, let's say, completely full of electrons. Each band has a certain capacity. How much capacity does it have? Remember, I made a statement that if you take 2 wells and couple them together, how many states you get? 2. If you take 3 or 4, you get 4 levels. If you take n wells and couple them together, how many do I get? N. So what is my capacity here? I have n levels, n possible values here. If you take an infinite, then of course this whole band is a continuous, but it's not really continuous. In realistic cases, I have a finite size, I have a finite number of atoms, and therefore each band has a finite capacity here. How many electrons can go into there? Okay. So if you have a certain number of electrons, first all the electrons will fill up this particular band here. Then they will go ahead and fill up this band, and then the next, and so on and so forth, depending on what the nature of the system is. So let's take a band here, okay, some lower band here, and obviously it will be completely full of electrons, okay, full of electrons here. Now this is something which is very important, that here is a band, right, which is full. I have lots of electrons that are there, and the statement that I'm going to make is these electrons here do not contribute to current conduction at all. They cannot contribute to any current conduction. All the electrons that are there in this band, and this band is completely full, they cannot contribute to current. Everybody can see? Qualitatively, here is a band. Note that the difference between the two bands' energies are large, right? If I go into a real crystal, let's say, each bandwidth may be, let's say, 0.5 eV, 1 eV, or 2 eV, something like this. And the difference between two bands that you see are forbidden is also of the same order, 1 eV or whatever, right? Is something of that. So here is a band which is completely full, right? Now I can write down a general expression for current as follows. Current will, let's focus on this band only, which is shown here, right? Which is shown here. All these states, different states means different values of K. Okay, different values of K, different values of energy. So I have a series of K values which are there, and all these K values, electrons are occupying the entire K values here, entire energy values here. Everything is occupied. The current I can write as minus Q times the velocity of a particular electron, Vj, averaged or summed up over all the electrons here. So I'm looking at N is the number of electrons per unit volume. Okay, I'm looking at one centimeter cube volume here, and N is the total number of electrons in that volume, and V is the velocity of an electron J, whatever is the velocity, and summed up over all the velocities will give me J. All right. Agreed? You can. So that's J here. So now, if you look at this picture, this whole band is full of electrons. So for every electron that is moving in a certain direction plus K, look at the symmetry. There's an electron which is moving minus K here. Velocity is what? 1 by h bar del E by del K. Velocity is that. So for every electron moving in positive K, there's an electron moving in minus K. And therefore, what will this sum turn out to be? 0. This sum will turn out to be 0. What this is telling us is the following. A band which is there, which is completely full, cannot contribute to current conduction here. An energy band completely full with electron does not contribute to current. So if here is a band which is completely full, as far as my electronics is concerned, I can totally ignore it. It will not carry current. Similarly, if this is completely full, it will not carry current. If this is also completely full, it will not carry current. It will sum up to be 0. Okay. So if I have a series of bands, then what it is telling us is if I have a series of bands in E versus K, this is completely full, this is completely full, this is completely full, this is completely full, and this is completely empty. Suppose I have a picture like this here. So this will not carry any electrons, cannot contribute to current. This cannot contribute to current. This also will not contribute to current. This also will not contribute to current, but the next one above it is empty. And there is a possibility, if the gap is small, that some of the electrons from here may go here. And therefore, I can get this to be partially full. And I can get this to be partially full here. So the bands which are of interest in semiconductors are these ones that I've drawn in color here. The topmost fill band, and after that, the band above it, which is empty here. All the bands below that are of no interest to me. Because you may be thinking that, can I not promote an electron from here to here? Well, the gaps are too large. The gaps are too large, and it's not realistic at room temperature to expect anything happening between here and there. So they remain full, they remain full, and they remain full. Of course, if you take let's say a very ultraviolet photon, UV photon or a high energy photon, that photon can come and knock an electron from here and promote it here. That's possible. Okay, but only under certain very special conditions you will find. Apart from that, these bands remain full, and they have no role to play in our electronics here, and therefore we don't bother about them. We only bother about the topmost fill band, which is valence band, and the band above it is the conduction band here. And therefore, the band picture that we draw is only the simplified band picture that you see. We show only the topmost valence band, which often looks like this here, and the band above it, which looks like this here, conduction band. Okay, so that's the picture that we draw. All the bands below that, we just forget about it. Okay, it's not important. The distance between the energy difference between the top of the valence band and the bottom of the conduction band is what we call as the energy gap here. All right. Okay, so that's the other thing here. An energy gap that you're familiar with. Silicon has 1.12 eV. Germanium has 0.67. Different materials have different E versus K relationship and different gaps here. Gallium arsenide has 1.42. Diamond has 6. Carbon in the form of diamond has an energy gap of 6. So it's practically an insulator with a very, very large energy gap here, gap of 6 here. Okay. Now, out of this is what we are getting is the concept of a hole also. And that's where I'll stop. So we have a band here which is completely full. Okay. And here is a band normally in a semiconductor which is completely empty. But now we said there's a possibility of taking an electron from here and promoting it here. Okay. Thermal energy is often enough to do that, at least in some amount. So I get an electron here and I get a vacant state here, empty state here. Now, note, let's look at the focus on the valence band here. The current now, which is, I've taken only one electron, and which electron? The kth electron, let's say. I have n number of electrons per unit volume. I've taken the kth electron and promoted it here. So my current carried by the valence band is equal to J minus Q sigma Vj summed over all the electrons except the kth. That kth electron has lost, is gone to the conduction band here. So now I'm talking about current carried by all the electrons in my valence band, right? Which is given here. Now what can I write it as? I can write this as minus Q, which is same, sigma summed over all the electrons minus the velocity of the kth electron. And what is this term? 0. Right? This term we've already said the summed over all the electrons is 0. So what do we get? J equal to plus Q times Vk. So that's what it is telling us. Now the band theory is telling us that current carried by all the electrons in my valence band except for that missing is equivalent to, or it can be modeled as, current carried by that missing electron, but if you associate a positive charge with it. And that's the concept of a hole. So the current carried by, so you don't need to bother about all these n-1 electrons that are there. The motion of n-1 electrons, the entire motion or the entire current carried by n-1 electrons can be modeled as a particle with a charge plus with the same velocity as Vk. So that's the concept of a hole here. Okay. So when we talk about valence band here, I have it almost completely full except for a few vacant states. I don't need to bother about electrons there. I can do my calculation not in terms of those large number of electrons, but I can do my calculations in terms of those missing electrons here. That's much more economical. You see, I have 10 to the power 22 electrons here, right? And the number of missing states are typically maybe 10 power 15, 10 power 16. So more economical to focus on the missing ones and rather than the ones which are present, and they give the same result here. Okay. So that's where the concept of a hole is coming from. And henceforth, after this particular slide, even though you realize that the effect of the entire band can be modeled in terms of the holes here, we will think of hole as a particle, as a real particle with a positive charge Q. That's it. Okay. After this, we will not go back, oh, it, is not real. You're seeing that the effect of the entire electrons can be modeled in terms of holes. And every experiment that you do, it sort of indicates that the hole is like a real particle. Okay. So after that, we'll not bother about a missing and thinking of hole as a missing electron. We'll keep on saying hole is like a positively charged particle here with plus Q and do it. So in that sense, whatever I do with electron, the same thing is valid with holes, except that it has a positive charge Q. Okay. So let's stop here and then.